Welcome to the fourth and final video in a series of how to solve quadratic equations, converting non-quadratic equations to quadratic equations. Before we get into the actual converting of equations from non-quadratics into quadratics, let's look at a quadratic equation such as this one. If you watched video 3 in this series, you'll recognize this as an equation that we could use a quadratic formula to solve. No mystery there. Here's something worth mentioning. This x is an x to the first power. And while we've never specifically brought that up before, it becomes relevant in this video. So let's take a closer look at the exponents in the problem and focus on those. The quadratic formula specifically only works when these exponents are a 2 and a 1. If they're anything else, the quadratic formula doesn't apply. So mathematicians were interested in discovering what would we do if those exponents were anything other than a 2 and a 1, say a 3 and a 1, or a 3 and a 2, or a 4 and a 3, or a 6 and a 2, or any other combination of numbers. Well, in general, mathematicians were never able to find a general solution to solve these problems. There were certain circumstances in which some of them were solvable, but they were never able to generalize and come up with something like the quadratic formula to solve them. But there is one specific kind of problem among these that mathematicians developed a really interesting trick for. This equation on the bottom here, where the exponents are a 6 and a 3, is easily solvable. And one thing mathematicians discovered over the years is while there is no general formula when these exponents are anything other than a 2 and a 1, they did notice that if the larger exponent was exactly double the smaller exponent, that there was an amazing shortcut that they could make to solve equations like this. Today's video is devoted to this specific case. What do we do when the larger exponent is exactly double the smaller one in a situation like this? And because we've developed this problem so far, I'd like to make this problem our first example. All right, so let's take a look at this particular problem. So what mathematicians struggled with initially is what do we do when we have an x to the 6th power or some other power other than x squared for which they had already determined the quadratic formula would work? Well, they had kind of a clever idea, which is going to sound strange at first, but what they did is they replaced that x to the 6th with x cubed squared. And you might ask, well, that seems to unnecessarily complicate the problem. Why on earth would anybody want to do that? Well, here was their clever logic. By rewriting x to the 6th as x cubed squared, they were able to then realize that x cubed appeared twice in the problem now. And that may not seem like an immediate benefit, but when you see the following trick called the substitution trick, you'll see why it benefits the solver to have the same thing appearing twice in the problem. So the mathematician's clever idea was, let's rename that thing which appears twice in the problem. For some reason they chose the letter U. I don't know why they chose that particular letter. It really wouldn't have mattered. But the idea is that if we let U equal x cubed and just make up some new letter and insert it in the problem, I can then take this problem that has x cubed appearing twice and replace each x cubed with my newly chosen letter, say U. And the reason this is a benefit is the following. Look at the top of the screen at the original problem. That is not a quadratic equation. Quadratic equations don't have x to the 6th in them. But look at the last line that we just put up, the 5u squared minus 42u plus 16 equals 0. That line is a quadratic equation. And therefore, we can use the quadratic equation to solve for u. So what I've done here is done just that, and at the end of a lot of scratch work, I ended up getting two solutions for the letter U. If you're relatively comfortable with the quadratic formula, then you accept this as something that you could easily do yourself. If you're scratching your head wondering where on earth did any of that come from, then get ready to pause the video and scrutinize all of my scratch work, which is right here. Okay, moving on. Now we've used the quadratic formula to solve for u. But here's the problem. No one ever asked us to solve for the letter u. As a matter of fact, the letter u isn't even in the original problem. It was our own creation in the solving process. But the good news is, now that we've solved for this self-created variable in the problem, I can take the fact that u represented x cubed and replace the u's back with x cubes. And now I have equations with x in them that I can solve. Okay, so to solve these equations for x, I would apply the cube root to both sides. That isolates the x in both cases, and I'm more or less done with this problem. Let me make a couple of comments about each of these answers. First of all, this radical is not something that you can simplify. Without a calculator anyways, there's no fraction which when cubed is 2/5. Now a calculator will work it out as a decimal, which I did here, although in an algebra class, because we don't tend to focus on decimals, we would just leave the answer in radical form and not put that decimal. On the other hand, the cube root of 8, which literally means that number which when cubed is 8, is 2. And you'll notice that makes sense because 2 times 2 times 2 is in fact 8. And so now I have my two solutions to this problem. Now even though I'm done with the problem, I just hit you with so much information. I think that might benefit you if I summarized everything that just happened in more general terms. So what happened in this problem? Well, first, I converted my quadratic equation, my non-quadratic equation, into a quadratic equation using a different letter, for which u is the traditional choice. I then solved that equation for u using the quadratic formula, and then I put back what u represented in the first place, which in this case was x cubed, and then I continued to solve for x from that point. Here's another example. The first thing worth noting in this problem is that if we take a look at the exponents, we have the same condition we had in the last problem, that the bigger exponent is exactly double the smaller exponent. If you're not real comfortable with fractions, take a minute to convince yourself that 1/5 is twice as big as 1/10. And so because we have this doubling phenomenon, we can use the same strategy that we used in the previous problem. So what I'm going to do is I'm going to take the x to the 1/5 power, and I'm going to replace it with x to the 1/10 squared. And again, this may seem really strange. Why would we want to complicate the problem like that? Well, by doing so, we have created a problem in which x to the 1/10 appears twice. The fact that it appears twice is very meaningful. Reason? Because if x to the 1/10 appears twice, I can replace it with any letter I want. U is the traditional letter to use here. And so I'm going to replace each x to the 1/10 power with u. And now I can use the quadratic formula to solve for u. It turns out when I do that, I get two answers for u. If you're not comfortable with the quadratic formula and you'd like to pause the video and see the details, get ready to do that. Here are the details. And beyond the details, I have to be honest here and say I didn't actually use any of those myself. I used the factoring method to solve for u instead. Remember, the factoring method is a viable method as long as you have a factorable trinomial, which we did in this case. Either which way, we now know that u is 1 or u is 3. But remember, my goal wasn't to solve for u, my goal was to solve for x. And so I have to remember that u was a replacement for x to the 1/10. Therefore, I should replace these u's with x to the 1/10 before continuing to solve. Now, in order to solve for x here, I'm going to raise both sides of these equations to the 10th power. For some of you that may seem obvious why I would do that. If not, watch this. Notice that if I raise the left side of either of these equations to the 1/10th power, I'm multiplying that thing by itself 10 times. And recalling the rule that when we multiply, we add exponents, adding up all those exponents gives me 10/10. 10/10 is 1, and x to the 1 is itself. That's the reason why raising both sides to the 10th power is a clever idea here. So when I raise both sides to the 10th power, this is what I get. And now I can simplify each of these answers. 1 to the 10th power is 1, and 3 to the 10th power worked out to be 59,049. Let's take a look at our final problem here. This one looks a little different than the other two. Before we really get into it, I'd like to point out that I could rewrite the equation this way, if I wanted to. First of all, because x is the same as x to the 1, but also because radical x is the same as x to the half power. If you didn't know that fact, that's just a fact worth knowing. And therefore, if I rewrote the problem this way, and took a closer look at these exponents here, I would notice that as in the previous cases, the first exponent is double the second exponent. 1 is exactly twice as big as 1/2. And I could continue to solve this problem the same way I did the previous fractional exponent problem, and there would be nothing wrong with that. But just to show you a slightly different perspective, I'm going to do something different. I'm going to exploit the fact that radical x squared, if you work it out, is the same as x as long as x is positive, and we'll talk more about that later. But why would this be relevant to this problem? Well, look on the left side of your screen. Notice that I could therefore replace x with radical x squared, because x and radical x squared are the same thing. Now, why on earth would anybody want to complicate or make the problem look uglier than it was to start with? Here's why. Because by choosing to do that, notice I have gotten radical x to appear twice in this problem. And that's a benefit, because if I can get radical x to appear twice, I can replace both radical x's with a new letter. And again, the letter u is the traditional letter to use here. Any letter would work. And so notice I've replaced both radical x's with a new letter, u in this case. Okay, now I can take this equation on the bottom of the screen and solve using the quadratic formula or factoring, depending on if it's factorable. It turns out it is, and I used the factoring method, as you can see on the right side of the screen here. I used the factoring method to discover that u is 4 or u is -3, two solutions for u. But let's not forget that it isn't u that we're solving for. In fact, there's no u in the original problem. So what I need to do is replace both of these u's with that thing which they were replacements for in the first place. And remember, since u represented radical x, then both of these u's should turn back into radical x's. Now that I've converted my equations back into x's, all I need to do is solve for x, and I'll have my solutions. But let's look at the equation on the right here, radical x equals -3. That's an unusual equation and turns out to be a non-solvable equation. The radical of any number can't equal a negative. By the way, not to be confused with taking the radical of a negative number. You can do that using imaginary numbers. But there's clearly no number x could be for a radical to equal a negative, because by definition, a radical is always positive. So that equation on the right has no solution and isn't worth consideration. That leaves us only with the first equation on the left, radical x equals 4. For that, I can square both sides to cancel out the radical, and I now have my solution for x. And that concludes our third and final example, and also concludes this 4-video series on quadratic equations.